Hello, this is Piotr Przybicin. In this video I will present our latest software. Specifically, it's about the Hvac Fem Simulator program. It is a program that is currently available from within the program and Xchart. Therefore, to use it you must first download the program and Xchart itself, and then use this button to launch the main window of the Hvac Fem Simulator program. Today's presentation or training is divided into several main points, which I present here in this agenda. First, I will generally explain what the Hvac Fem Simulator program is used for. Next, how to input calculation data and what the main calculation modes look like. I will also show how to conduct sample calculations based on an object we have essentially implemented, and how to interpret the results of such a simulation. We will also show how to generate, or if it's possible to generate, calculation reports. And at the very end I will talk a little about the licensing method, what the current status is regarding obtaining a license for this software. So okay, now I will explain what the program is used for and how it is built. So as I said, this is what the main window of the program looks like. The program is built from three main modules of temperature and humidity, where we can actually perform very interesting simulation calculations, where we can analyze many variants of ventilation and air conditioning systems, from simple to very advanced, also considering heat recovery, moisture and air recirculation. We can check here how the temperature and humidity of the room will change depending on the air supply scheme we impose. We can perform calculations in such a way that the program calculates the supply parameters itself to achieve the parameters we want in the room. We can perform calculations for ventilation considering heat accumulation in partitions. We can also perform calculations for adiabatic cooling, examining the impact on indoor parameters. Next we have the carbon dioxide concentration calculation module, which allows us to simulate the dynamics of carbon dioxide concentration increase depending on the number of people, the amount of ventilation air, and the ventilation operation scheme. And the last module is the module for calculating overpressure or underpressure inside the room, depending on the known volume, the amount of supplied air, the number of leaks or contact openings with other zones. However, I think the flagship element and the most developed at the moment is the temperature and humidity module. Generally, we still consider this program to be a kind of a really big step forward when it comes to HVAC software, because it allows us to analyze HVAC systems over the entire year for a full set of climate data. The psychrometric chart, for example, allows for the analysis of a small segment of reality here, where we input certain specified parameters regarding the intake air and analyze what needs to be done with this air to ultimately achieve the desired parameters inside the room. However, this is for the combination of two initial parameters. Here we can conduct a full analysis for all climate data for 8,640 hours in a year, and study how this will translate to the parameters inside the room. I am starting our first module, and now what we see on the screen might frighten some people a bit regarding the amount of data that needs to be entered. However, I assure you that most of this data is repetitive and it's not as daunting as it might seem at first glance. Here we have, maybe I'll talk a little about the general assumptions. Here we have a layout of our room where we assume that we have certain equipment which is subject to specific heat accumulation. We have certain sensible heat gains and certain moisture gains inside the room. Here we have a cross-section of this room. And that the whole trick is that we need to define the partitions of this room, taking into account the windows in order to calculate, of course, the heat and moisture gains from the partitions. Also, the gains released by the equipment located in the given room, here we generally have our main menu where we choose what should be included in the calculations and what should not. We can freely check or uncheck options. Then the amount of data we need to input automatically also changes. Here we have our working mode, or perhaps the calculation mode of our simulation, and the data we need to input. The data we input also depends on the calculation mode we are performing. The simplest of these modes is the const mode, which is the mode where we assume that all air parameters, whether it's the supply air, heat gains, are simply constant at a given moment, and we calculate or simulate what impact this will have on the parameters inside the room, where we define the air parameters in the room as initial at this moment, and measure what will happen to them if we have specified heat gains or an airflow with a specified temperature and humidity. This is the simplest of all these modes. And what can it be used for? For example, we assume that we have a room that has been unused for a long time. Suddenly we turn on the ventilation or air conditioning mode and see how long it takes for the room to reach a specific temperature that interests us. So, I don't know, a conference room on a sunny summer day, standing without air conditioning, we need to prepare it within a certain time for use, so that a group of people can be let in, and we measure the time when, and we study the time when the temperature stabilizes at a certain level that we expect. However, these are the simplest possible calculations, and it is known that all these heat gains or airflow, supply, and its temperature are defined as fixed input data. More advanced calculations involve defining all these parameters as a profile. So we decide how much air is supplied in a given hour, what its temperature is, what its gains are, and what, let's say, the temperatures and humidity levels are on the opposite side of the ventilation barrier. But we will get to that in a moment. First, I will describe the parameters that need to be entered as input data. Therefore, what we enter as output data is the atmospheric pressure for which we will perform the calculations, the total simulation time, and the time step. Generally, these parameters can be modified freely, and the program tries to independently suggest the most optimal time step and simulation length. However, if we are examining a single day individually and so on, we simply adjust the time to suit our needs. And we can do this freely here. However, there is one caveat. We must choose the time step so that on one hand the simulation does not take too long, because the shorter the time step, the more calculations will be performed in the loop and the longer the simulation will last. However, a time step that is too long will cause the simulation to be short. The results may then be less accurate, and the simulation may even be unstable, but in such a case, an appropriate message will simply be shown indicating that the simulation was unstable. In connection with the above, it should be adjusted appropriately to the length of the entire simulation time. As a consolation, I will say that the program independently suggests how long this time step should be, depending on the duration of the simulation. And such a time step is selected automatically, although sometimes it happens that despite this, the simulation may go beyond some stability range. And then this time step needs to be manually reduced, which will of course here covered by an additional prompt from the program. Next, here we provide the initial parameters of the room and its humidity, which are the parameters we start with. Depending on whether we are simulating cooling or heating, we can modify these parameters. We can calculate, for example, how quickly we will cool a room to a specified temperature if it was heated, or if it was cooled, how quickly the room will warm up if we heat it using an HVAC system. Next, jak sam pak macie, we provide the main parameters concerning the room itself, geometric ones such as length, width and height. Based on these parameters, the volume is calculated, treating the room as a simple cuboid. And these calculations, as you can see here, update automatically. If, however, we are dealing with a room that is not a perfect rectangular prism, we can manually modify this volume, and it is then used for calculations. Here we have the infiltration indicator given or defined as a percentage of the room's volume. So here, in other words, here having specified 0.1 exchanges per hour, it is related to the volume. So in this case, the infiltration is 50 cubic meters. All the information we enter here updates on our drawings, diagrams. So here we have the height, here we have the width, the depth. Similarly, we have heat gains, which we enter here, moisture accumulation, everything is updated. If we calculate with a constant temperature of the supplied air, it is also noted here that it is a constant temperature and constant humidity. If we calculate according to other parameters, then it will be provided here as functions, for example, of time. Okay, let's move on. Here we also provide the temperature of the infiltrating air, meaning, in other words, some external air flows into our room through leaks, and here we provide its temperature. Here, for example, 30 degrees is given. Next we define what internal heat gains we have. Here we specify 5 kilowatts and 1 kilowatt, 5 kilowatts of sensible heat gains and 1 kilogram per hour of moisture gains. Here we similarly specify what parameters we will supply to the room. Its flow rate is 4,000 cubic meters per hour. Here we have a temperature of 14 degrees and 90. Here we need to enter 4,000, and here we can see it updates 4,000 cubic meters per hour of supplied air. Here we have the parameters concerning the room's equipment. If the room has any furniture or some material, we can define the parameters of this material here. It is given as one averaged value. So, well, if it is some kind of composite material and so on, unfortunately we have to rely on averages. So here we simply provide the heat capacity of that material. Here in our always present suggestions, bubbles appear showing what we can enter here: the mass of this material, the density of this material, the initial temperature, the initial relative humidity, and the typical water vapor diffusion coefficient. Based on this, the heat flux released or absorbed from the room through the storage material, that is the equipment, is calculated, and the release and absorption of moisture are also considered, meaning counting systems with humidification or air drying. Here, an additional factor also appears related to the absorption and release of heat and moisture by the material equipment accumulation. Here we define the geographical parameters, and this is important because if we perform calculations considering partitions, the program will, for that specific day, account for heat gains from sunlight through the windows, so they should also be specified. And here we enter the data concerning the partitions themselves. As you can see, there is quite a lot of this data, but it is entirely repeatable. So here, as I said, at first glance it looks quite complex, but in reality it's about providing in each of these fields simply the definitions of parameters that define the partition. And here for the roof, for example, we provide the total area of the roof partition, including skylights. Here we provide the area of the skylights, and this area will be subtracted from the total area of the roof. Then we provide the heat transfer coefficient for the roof partition, the heat transfer coefficient for the skylight. Here we provide the temperature on the other side of this partition. If we calculate according to the coast mode, we define these parameters here. If we choose the profile or profile plus climate, then later we will see that these parameters are grayed out, and this will apply not only to the temperature on the other side, but also to heat and moisture gains, supply air temperature, and so on, because these parameters, when calculated according to these modes, are parameterized, and we will define them separately for each hour. However, when performing according to the constant mode, assuming that all these parameters are constant on the other side, we must define them here. Here is the thickness of this partition, the density of this partition, and the coefficient specific heat determining the total thermal capacity of this partition. What is important from the perspective of heat accumulation, here is the water vapor diffusion coefficient, which is important from the perspective of moisture accumulation. And here we provide the total coefficient of solar radiation transmittance through the skylight. For the base, and of course we also choose the type of this partition, whether it is external or internal. If we choose that it is an internal partition, then the total solar radiation transmittance coefficient in the calculations will be considered as 0. There will simply be no heat gain from sunlight because the partition is internal. We have gone through one partition, and the remaining partitions look similar, except that for the floor or ceiling, we do not have the option to define windows, because the assumption is that there are no windows through the floor or ceiling. However, we define the partitions here: north, south, east, and west. If any of these partitions is deviated from the direction, let's call it north, then we select, we choose the azimuth of this partition accordingly. This applies to each partition separately, and that's basically all when it comes to providing these main parameters in this window. However, a certain difference arises if we calculate according to the profile or the profile with climate. So with climate, the difference is that while here we provided constant heat gains and air supply, when calculating according to this, we can define these parameters as a variable throughout the entire day. And here, after selecting this or that option, the time variables button appears, and in this situation we simply have to define those parameters which we previously defined as constant and which are now grayed out separately for each hour. And this applies to both heat gains, moisture, supply airflow, supply air temperature, and supply air humidity, as well as external parameters such as external humidity, external temperature, on the side, the temperature on the opposite side of the northern partition, the temperature on the opposite side of the southern, eastern, western partitions, as well as the roof and floor. If we create, let's say, our own profile of time variables, we can save it as a file and later open it in other projects as input data. We won't have to fill in all this data here. If we wanted to modify some parameters here in a group, let's say we want to change gains and we don't want to define them individually, we can simply enter them in this window and copy them to the remaining hours to speed up the process of providing these, defining these variables. Here, much similarly, we also have buttons for copying these parameters downwards. And now it's also about speeding up the input of certain data. If we have all the external partitions, then if we enter, for example, the external temperature here, whether it is 35 degrees or some other temperature, can then be quickly copied to the other partitions. We don't have to do it individually, as that would take a lot of time. Additionally, if we select the tag profile plus climate, what changes is that the parameters of the time variables related to the external climate are grayed out. This means we cannot define them because they are automatically pulled from the climate data file that we select and define in this window. So here we define only those parameters that are in the white fields, and honestly these calculations are the most advanced, taking into account the climate data, and also the most interesting in my opinion. Here, however, we have the operating modes of the ventilation and air conditioning system itself. And here we can perform calculations such as examining how with specific heat and moisture gains, as well as here with the specified assumed supply parameters, which we define here, the temperature inside the room was maintained. So if we define it here as plus 22 and 50%, and then choose climate data, for example, Poland, and for example, Bydgoszcz, the program will automatically determine the latitude of this city. However, there is one caveat here that the program must have internet access because this data is retrieved via an API. Here we define the dates from when the calculations are to be performed, and we can calculate, perform a simulation to see what will happen with the indoor air parameters and indoor humidity for the given variables, and of course climate data. If we have a profile, we need to define this data. Let's call them climate or external for the other partitions ourselves. For example, you can use it when you have a ventilation system that is underperforming or something is happening with it and you want to check why. Or if you have some exceptional climate data that do not occur under normal conditions and you want to test how the system will handle such circumstances. Okay, so here we select, as I said, the calculation mode, and we can calculate it according to a constant temperature. Maybe not according to a constant, but according to the supply air temperature and humidity and relative humidity based on time variables here. We can also perform calculations for ventilation, considering the accumulation, of course, of heat and moisture in the partitions. In this situation, here we see that I selected a profile, so maybe I'll choose the climate as well. Okay, and now in such a situation, when we calculate ventilation, we assume that the parameters of the supplied air are equal to the parameters of the outside air. So they will also be taken directly from the climate data file. So here they are also grayed out. Previously they were to be defined by the user. Now they are gray, so what remains is the definition of heat gains and the supply airstream. Next we have fully automated calculations where we slightly change looking at calculations, at simulating. Here the room temperature and humidity will depend on the airflow, and we really don't know what we will achieve. We only know what we are supplying, and what we achieve will be our result dependent on the airflow and gains. This mode allows for full automation of calculations, and that means in this situation we define what we want to achieve in the room, what temperature and humidity we want to control, additionally defining the parameters that the system can achieve, the lowest airflow parameters and the maximum airflow parameters. So here for cooling, here for heating, and what will be the minimum temperature of the cooler wall that the system can assume in calculations, depending of course on the type of refrigerant. Will it be direct evaporation? Will it be a chilled water unit? And so on. However, here the system will automatically adjust the supply air temperature and relative humidity to achieve the parameters we set. And this is really a very interesting feature because it allows us to perform simulations of complete air conditioning systems while maintaining temperature and humidity, and observing whether it will be possible with such set parameters or not. Can we? Do we need to change anything in our system to achieve such parameters? Also, these calculations are exceptionally helpful for all kinds of spaces, like clean rooms, museum type laboratories, anywhere we need to control both temperature and humidity. These calculations will be incredibly helpful for us. Here we have a similar calculation mode with the small difference that here the relative humidity is no longer controlled, only the temperature is controlled, while the relative humidity inside the room will be resultant. In connection with the above, these are calculations more related to air conditioning comfort, and here we have calculations concerning full air conditioning, and in this case, while performing these calculations, we will be dealing with two supply air temperatures. One supply air temperature, which will be necessary from the perspective of maintaining humidity, and a second supply air temperature, which will be necessary from the perspective of maintaining temperature. Meanwhile, the difference between these supply air temperatures will in fact be the temperature that must be covered by the secondary heater for regulating relative humidity. Because the dehumidification process involves deep cooling and then reheating this air to the supply temperature, which is necessary to additionally remove heat gains from the room. There is really a lot of fun with these calculations. And the last calculation mode is the mode related to adiabatic cooling. Here I think it will also be very helpful as there is a lack of tools on the market that allow for reliable analysis of how such adiabatic cooling systems work, what we can achieve, what it depends on, and how the relative humidity of the air in the room will be shaped. So this is really a very interesting tool here as well. Here we define the water saturation coefficient of the supply air, which is implemented in the spray chamber, in the adiabatic chamber. Here, by selecting this mode, I will show one thing, that here we can additionally choose during which hours the operation of this adiabatic cooler is allowed and when it is not. In other words, if we, for example, uncheck a few night hours in such a work mode, it will mean that at night 4,000 cubic meters with parameters equal to on the external air parameters will be directly supplied to the room during those hours. However, for the rest of the time, air will be supplied to the room, which will already be cooled by the adiabatic cooler. However, returning to this to the same function, if we choose, for example, the automatic parameter calculation mode, then in the time variables, we will also have the option to disable, for example, the climate control hours. In other words, during these hours, the system is prohibited from operating with climate control, meaning the heater, cooler, or humidifier will not function here. Simply outside air will be blown in here as it is without any treatment. However, during the remaining hours, the system's operating mode will activate, taking into account the full operation of individual sections to maintain the parameters we set in the room. However, if we want the system not to work at all during these hours, then we must, of course, enter 0. Okay, this is roughly how data entry looks. Here we can additionally account for heat and moisture recovery and recirculation in our calculations. If we have some system in our ventilation system, heat recovery, then we can define its parameters here, and it will be included in the calculations. Although on the temperature chart it will not have any impact, it will affect the heat and cooling balance charts and so on. So here we need to define it. One important thing is to look at the extracted airstream, meaning if we have the supply airstream defined here as 4,000 cubic meters per hour, then we need to manually add how much of this air is being extracted from the room. And that's a brief overview of the data entry method. Now let's move on to the next point, namely performing a calculation example. I will use a file here that I have previously created, and it is part of an actual project. This is a museum object in Poznan, where the goal was to maintain a temperature of plus 20 degrees and humidity of 45% inside the room throughout the year for the safety of the exhibits. And we somewhat used the trial and error method to adjust the operating parameters of the system so that these parameters were maintained. So we set that the minimum temperature the system can achieve at the supply is 10 degrees, meaning the temperature difference between the room air temperature and the supply temperature cannot be more than 10 degrees, hence a minimum of 10 degrees at the supply. The temperature on the supply air cannot be higher than plus 35 degrees, and due to air drying, we have set the temperature of the cooler wall at plus 5 degrees Celsius. The room is characterized by dimensions of 36 meters in length, 44 meters in width, and 7 meters in width. Volume it is a room with a rectangular prism shape, rectangular prism geometry, volume 11,088 cubic meters. Small infiltration due to high tightness, and gains defined in a way. In such a way, in the form of a profile where we have the operating hours of the facility from 7 to 16, where visitors generate certain constant heat gains, which we calculated at 23 kilowatts, and these are mainly gains from lighting and gains from people present there, and moisture gains. We will record 13,000 cubic meters per hour there. And here, two of these walls are internal walls. So if we choose internal here, then we will have the possibility to define the parameters on the other side of the partition. If it is an external partition, then everything is simply taken as given, meaning as temperature from climatic data. Let's mark these as well, because I showed them earlier, I unchecked them. Okay, and now we can proceed with the calculations. So our goal is to achieve a temperature of 20 degrees and 45% throughout the entire year. We perform calculations from the 1st of January to the 31st of December.
Yes.
And here, immediately performing calculations before our eyes, the results of this simulation appear in the form of temperature, humidity, absolute moisture content, as well as here the room's heat balance, room's moisture balance, gains, heat losses through partitions, individual partitions, and results concerning the internal surface temperature of partitions. Let's wait until the simulation is complete to talk a bit about the results. We are performing, as you can see, calculations here with full climate control, and here will be an interesting thing regarding the distinction between these two supply air temperatures, the temperature for dehumidification and the supply air temperature for removing heat gains. Okay. The simulation has finished. Here we have a window with the results, which we will get to in a moment. And now a moment on how to navigate the charts. So here we have buttons to maximize and minimize the chart window for better viewing of the results. If we are additionally interested in a specific part of this graph, we can enlarge it by clicking the left mouse button and dragging the window from left to right. Then those areas will zoom in and we can view them. And now a few words about interpretation. Here we can also turn off individual parts of this chart. This is the temperature of our room. As you can see, it is a straight line, and therefore it only means that the system was able to maintain this temperature throughout the year for the air supply parameters we set. Here we have the temperature, the graph of the variability of the outside air temperature. Here we have a graph of the supply air temperature necessary to maintain the assumed temperature of plus 20 degrees in the room, in this case. And here we have the temperature that is necessary to maintain the relative humidity in the room, which we set at 45%. Huh? And what do we see here? We see here that there are moments, when I turn off these two graphs, that there are moments when the temperature of the supply air, due to dehumidification, would have to be lower than the air temperature necessary to maintain the temperature. And this difference here actually shows us the efficiency or the temperature difference that must ultimately be covered by the secondary heater, because the process of condensation cooling involves first deeply cooling and then secondarily reheating the air to achieve a specific relative humidity.
So in my opinion, it's mega
an interesting and engaging tool for engineers, because look, it even gives us extensive knowledge about when the individual elements of our system need to be ready to properly prepare the air to achieve the internal air parameters we have set. And here, for example, already in fact by March or April, we need to have the chiller ready so that it can properly dehumidify the air. Because by then, for such parameters, it turns out that the air needs to be deeply cooled and water condensed to achieve the required relative humidity. However, in the forest in the summer, we see here that for most of the time, the supply air temperature, that is dehumidification, is decisive. And here we will have to deeply cool and then heat to a temperature equal to the supply air temperature, which is necessary to maintain temperatures of plus 20 degrees. If we provided that temperature, we wouldn't maintain plus 20 degrees in the room. It would be too cold. Therefore, after drying, we need to heat the air to such a temperature. And the strength of these simulations lies in the fact that on the Molière chart, on the psychrometric chart, we are able to analyze, maybe not able, but usually we only analyze the extreme parameters of the outside air and do not see the whole picture of the situation. We don't actually know. And I personally have made this kind of mistake a few times, not fully realizing that drying would be needed. For example, at the turn of March or April, and then those parameters might not be maintained, which really has a decisive impact in some rooms. No? Okay, now moving further with the analogy, we have an analogous graph concerning relative humidity. Here we see that this relative humidity was also beautifully maintained throughout the entire year, and the absolute moisture content in the room, where we also see how it shapes here the absolute moisture content of the supply air, the room, and so on. We have here a heat balance chart. Here it is very shaded, so we can turn on or off individual lines that appear in the legend, indicating what they mean. However, from the user's perspective, I think the most important aspects here are the cooling heat and heating heat, as well as possibly the total heat gains. And here we see that here we have a graph of the amount of heat we need. It is all above zero, marked with red and red field, red lines. And here we have the cooling demand that is required. And for example, at the peak, we know that the heater will need to have power about 66 kilowatts to cover heat losses. And for cooling needs here, we will need to have power provided from the cooling source of 178 kilowatts. Here we see that heat is also needed in the summer for drying processes, and not only that, because sometimes the outside temperature in the case of this climate data can be lower and the air needs to be heated to achieve the appropriate temperature. Of course, then we can perform the same calculations considering heat and moisture recovery and see how it changes. And here we have a moisture balance chart. So here we see that during these periods we need to humidify gear. This is everything here that is above zero, is the system's efficiency, which humidifies the air for us to achieve a certain humidity. And here we see that the maximum humidification efficiency is about 92 kilograms per hour. Here we have, I don't know if there's anything more or not. We can zoom it a little less, so it will probably be around 92. However, the peak dehumidification power, water condensation, occurs here, and it is a capacity of about 153.5 liters per hour. That's how much water we will need to remove. This is the maximum dehumidification capacity the system will achieve. Here is also a graph of heat gains. So here we see through the individual partitions, the most of course is through the windows, through the individual partitions. And here we have a graph of changes in room temperatures, partitions. But for example, let's make an example that we want to achieve, in this case 40% using a cooler which has a surface temperature of the cooler plus 5 degrees Celsius, and let's check if we will still be able to achieve the relative humidity we assume, which is 40%. And in this case, do we possibly need to use a different dehumidification system? I'm thinking, for example, about adsorption dehumidification. So let's run this simulation again and see what happens.
Well, here we can already see that certain signs are appearing, indicating that this humidity cannot be maintained all the time, that there is already a bit of a lack of system efficiency, and here we can see some kind of jaggedness in this graph.
Which in other words means that a temperature of plus 5 degrees as the temperature of the cooler wall or the supply air, limited to plus 10 degrees, does not allow us to achieve the required relative humidity.
And in this case, we have two options. Either we lower the supply air temperature, or we lower the temperature of the cooler wall.
Of course, here we are also limited by certain parameters, because we cannot go below, I think even below 3 plus 3 degrees, because then there might be a risk that the cooler will freeze and frost locally, which is not a good idea. In connection with the above, we can determine a critical point where we must obligatorily switch to an adsorption drying system under certain parameters. Okay, so that's generally a brief overview of simulating. We can also, for example, currently examine how the temperature inside the room would change with the disks we have defined. If we were to choose, for example, air supply according to external air parameters, I will quickly perform such calculations.
And here everything is automatically calculated and drawn beautifully, as you can see. But maybe this doesn't make much sense for us, so I will stop these calculations and start the calculations related to humidity again. And temperature. And in a moment I will show how we export the results. Maybe a few more words about the results we obtain here. So PIF shows us what the final temperature in the room will be. However, this is the temperature we find at the very end of the graph. So in the case of simulating data, simulating or calculations performed according to the profile and climate, it doesn't necessarily reflect the end of the simulation, what will be determined there. It has the greatest significance here when performing calculations according to the const strategy, because it is a form of some exponential function that asymptotically approaches certain values, and then PIF makes physical sense. In such simulations, according to the profile or profile plus climate, we simply obtain the last data from the simulation that occurs there. Ti max is the maximum room temperature. Ti min is the minimum temperature that occurred during the simulation. If we are dealing with a case where the minimum temperature imposed by us is sufficient to cover all heat losses and gains, then we simply achieve equal parameters here. However, if we are dealing with situation where either the airflow is too small or the temperatures do not match, then we will have different values here as well. The same applies to relative humidity. This is also the last point here on the calculations and the parameters obtained during the simulation. And here we can already see that they are not equal. So our humidity fluctuated from 50 to 40% during our calculations. Yes, Tizen and the TI max here is taken as 50% because we set 50% at the input, and this is the first calculated value here. So if we define it this way, when the relative humidity stabilizes, we will simply obtain these types of parameters. Okay. Next we have the same parameters regarding the absolute moisture content. And here we have the maximum power of the heater that must be applied in this system to achieve the parameters we set. The total cooling power that must be provided from the cooling source to achieve the appropriate cooling, the appropriate parameters we want. Here is the maximum humidification capacity, maximum dehumidification capacity, and here is the annual energy consumption. Here we have heating energy in megawatt hours, cooling energy in megawatt hours. Here we have the total amount of water that must be supplied for humidification and the total amount of water that will be condensed over the year in tons. And finishing the simulation issue here, we create a calculation report in a very simple way, just by clicking this button. Here we provide data. We click OK, and here within a few seconds a calculation report should be generated. It looks in such a way that it contains all the information we entered regarding the room, ventilation, building partitions, and our time variables that we entered for the calculations. Here we have our screen with calculation parameters, and further on we have the general simulation results and graphs of temperature, humidity, heat and moisture balances, heat gains and losses through partitions, as well as the internal partition temperature. Here we also have a legend with all the variables used in the simulation, and that's generally what the report looks like. Alright, so now actually, as I said, there are plenty of calculation modes here. We can just as well calculate according to adiabatic cooling, so maybe at the very end I'll throw in such a simulation so you can see. That's the difference. No, I don't know if you know or not, but adiabatic cooling involves having a certain combination of external air parameters which we draw in, pass through a spray chamber with an appropriate water saturation coefficient or saturation. An adiabatic process involves perhaps an exchange, because here we are not dealing with heat exchange as such. Here the enthalpy of the air remains constant both before and after the spray chamber, while the proportion between sensible and latent heat changes. So we use water to lower the sensible heat but increase the latent heat, which significantly raises the relative humidity. And here each spray chamber is characterized by a certain specific saturation coefficient. Here we assume about 90%. It might be slightly less, but let's say 90% is a kind of standard. And consequently, for each combination of external air parameters, we will obtain a certain supply air temperature. And the limit here is the wet bulb temperature that we can achieve for a given combination of intake air parameters. So this efficiency of 90% simply tells us how much of this air will not actually undergo such humidification, or on this curve adiabatic humidification, where we stop. Okay, so as not to prolong, I am starting such a simulation, and here I will also show how it shapes up. Here we see our room temperature. Maybe, sorry, a little stop. We will conduct these calculations for 1 month. It will be faster, and the results will be just as interesting. And what do we see on this graph? Here in this intense blue, we have the parameters obtained in the room. Meanwhile, here we have the outside air temperature, and here we have the air parameters after passing through the spray chamber. So I might turn off the indoor air and show this difference. So this is the outdoor air, and this is the parameter of the supply air that we obtain after passing through the spray chamber with a saturation efficiency of 90%. So, for example, for the air that at this moment was, let's say, 25.5 degrees, it was cooled to a temperature of about 17 degrees using adiabatic cooling. However, one must be aware that adiabatic cooling itself has a significant impact on the increase in relative humidity, which must be considered when potentially discussing with the investor. Of course, there are methods to limit this relative humidity, which manufacturers introduce as the so-called humidity muzzle. However, generally, adiabatic cooling has the characteristic that it unfortunately significantly increases the relative humidity inside the room. However, there are many facilities where, firstly, higher relative humidity is required, and there are many facilities where this relative humidity is not a problem. And in such applications, adiabatic cooling can indeed be successfully used. And that's how it would be presented. Okay, and now briefly discussing these two additional blocks, namely calculating carbon dioxide concentration. Here the situation also looks very simple. We have a diagram where we provide the airflow. We can perform these calculations in two modes, either constant, where we define these parameters, or profile, where we then input our data regarding the ventilation system and the number of people in the room, variably, as in each hour of the day. However, when we perform these calculations, as a rule, we must input the supply air stream and the background concentration, meaning the concentration that the outside air naturally has. Here is the initial concentration present in the room before we turn on the ventilation system. The dimensions of this room, meaning the length, width, height, and the number of people in the room. Now, based on this, the program calculates the total carbon dioxide emission from people. Here we provide the total simulation time and time step units, and we can start the calculations and check for these 15 people, and for such a room, after how long the carbon dioxide concentration will stabilize, at what level. Here we see that 1000 ppm, which is considered a relatively comfortable value for carbon dioxide concentration in rooms, will stabilize after 3 hours. However, of course, if Pekishi, if it were a smaller room, hypothetically 1 by 1, the concentration would rise very quickly, and if it were a very large room, then the concentration would rise and rise and rise, and even after 10 hours it would only be 480 ppm, which we would have to extend the simulation to even longer periods to see when that value of 1000 parts per million will finally stabilize. Yes, when the same applies to this profile. If we wanted to introduce this data in the form of variables, let's assume there are periods when there are fewer people. Later a larger number of people enter, then again there is a smaller number of people. However, the ventilation airstream can be constant, can go. So in principle, we can also optimize some ventilation systems in churches where the entry of people is periodic, or in schools when there is a break, and run such a simulation. And then we see here we might extend the time and the time step. Then we see how it changes for us over a longer period.
Yes, and that would be basically it for this module. And in the last module regarding the calculation of overpressure and under pressure, it is also a very interesting tool, which is particularly useful in all rooms where there is a need for pressure gradation, operating rooms, clean rooms, laboratories, and such things. If we want to achieve overpressure or under pressure in these rooms, it is usually quite a difficult task, which this tool can help us with very well. Here we also choose whether we calculate overpressure or under pressure. We also provide the dimensions of the room as length, width, height, atmospheric pressure in millimeters, or the initial internal pressure inside the room, the stream of supplied air pressure outside the zone. This can be atmospheric pressure, or hypothetically it could be a second room here. Then we provide the size of this opening here, the contact one. I w Posi ideally we should know them, although it's not always possible. But let's say we know and we want to achieve a certain specified pressure difference between these two rooms. Here we provide the room density, time step, temperature, internal temperature, and time step. We start the calculations and obtain the result that by blowing in 1000 cubic meters into a room 10 by 10 by 4, we will establish an 18.5 Pascal pressure difference. We can do the same for negative pressure, also obtaining these results, and equally important, the dynamics of these pressure changes, which also allows us to estimate how much we actually need to supply to a given room for the dynamics to be appropriate in that volume. Okay. And generally, when it comes to the main features, I think I've covered everything. As for the licensing of the program itself, it is available here. The program is available in several options. The first is a subscription type license, and it is a single user license for 12 months without the possibility of transferring to other computers. This license is permanently assigned to the computer workstation. Then we have the OM license. It is also a single user, perpetual license, without the possibility of transferring to other computers. However, it is important to be aware that replacing the computer with a new one results in the loss of this license. So it is a perpetual license, but for a specific computer setup, as it cannot simply be transferred. Next, we have the LM license, which is a mobile license. It is a single station perpetual license, and here there is already the possibility of transferring this license to other computer stations using a license server. So in this situation it is very simple, because we use a license manager and simply enter the license number to transfer it to the server. On the second computer we install IXChart, enter the same key and download the license back, and we can exchange it on many computers. Now, the only limiting condition is that no more than one person can use it at the same time. And the box license for larger corporations, it is a 3-seat license, also perpetual, with the ability to transfer to
other workstations using a licensed server. Generally, I think that's all. So thank you very much for your attention. I hope I have clarified a bit about using the Hvac Fem simulator program. I warmly invite you to test it. Currently, the program is free to download and test until the 31st of December 2025. So anyone can freely use and test it. So thank you very much once again, and see you next time. Bye.